Hey everyone, happy Thursday. This is Sue Ewig, and I am excited to welcome you to another SageMaker webinar. We're going to cover the blazing text algorithm today. Our main presenter today is Pratap Ramamurthy. Pratap, you have met Pratap before. He's presented on these calls before. He's a partner solutions architect who works with our partners, helping them build their solutions on top of AWS. Just a little bit about Pratap. Prior to AWS, he was a researcher who worked on creating quantum dot lasers. He created test tools for web servers and optimized Wi-Fi using game theory. Currently at AWS, he focuses on machine learning, and he has a specific interest in natural language processing, hence today's topic. Joining Pratap today is Chris Grenek, again, who you've met before. He's just going to help get your questions answered. Speaking of questions, there is a question section on the right navigation pane on GoToWebinar. You can just feel free to pop your questions in there so Chris can kind of sort them and section them out and make sure that we get them all answered during the call. So let's jump right in. Pratap told me that this is his favorite algorithm, and I know he's excited to share it with you. So Pratap, take it away.
Oh, thank you, Sue. Absolutely true. This is a great day for me. This is my favorite algorithm, and I'm so happy to be presenting this algorithm to you guys today. Welcome to today's webinar. As I said, my name is Pratap Ramamurthy, and this is Blazing Text. Before we go into the webinar itself, this is the schedule for our webinar series. The previous one was Deep AR. This is the 6th in the series for people who have not been here before. Today is September 6th, and today's webinar is Blazing Text. My previous webinar was on sequence to sequence on 7/26, and the next one is on OCR, that's September 13th. All right. All right, welcome to this webinar, and today we're going to be talking the 6th algorithm in the Amazon algorithm series. But what are Amazon algorithms? Amazon algorithms are algorithms. These are popular algorithms that have been completely rewritten by Amazon for AWS. And these have been rewritten because we have optimized these algorithms to work efficiently on the AWS hardware, as well as to efficiently use the other resources that AWS has, like S3 and EBS volumes and GPU architecture. These algorithms can be consumed as a service, and the way you consume it is using our Amazon SageMaker's service. That's our main machine learning platform on AWS. All right. So in this, we have several algorithms in this, and today we're going to be talking about Blazing Text algorithm. This is one of the most important algorithms, or it solves one of the most important problems of natural language processing or computational linguistics. So what is Blazing Text? What does it do? This is the precursor step to doing any kind of natural language processing. Be it if you're, let's say, you're creating a text classifier that is trying to see if a text belongs to any one of the classes, or let's say if you're doing any kind of natural language generators. We saw sequence-to-sequence modeling in my previous webinar that also requires you to convert your words into vectors. Let's say you're doing sentiment analysis on text, you would need this. Or in general, any natural language processing task. Pretty much most natural language processing tasks require you to vectorize your words, and that is what Blazing Text is needed for. Let's look at what is the problem that it solves. What you're looking here is a 3-layer neural network. This is not exactly an accurate representation, but a logical representation of how a general neural network looks like. And on the left side is where you would send your inputs, and the input would go through the feed-forward process, and output would come on the other side through the output layer. Now, when you're looking at numbers, or when you're looking at device measurements, sensor measurements, you can input these into neurons. The neurons take a number, typically a number from 0 to 1 as input, or -1 to 1. And then if that is the case, how can you send text as input to a neural network. You cannot send text. It cannot consume. This has to be converted. The words in a sentence has to be converted into some kind of a digital version before it can be sent or used in any form of machine learning, right? This is what is called vectorization or embeddings, right? And there are several forms of encoding. Let's look at some forms and see what they are, how it's done, and what are the problems with this, right? A typical form, the first thing that can come to mind is integer encoding. Integer encoding means that you take a word, assign a number to that, that becomes an ID, right? Here, for example, we take all the words in the vocabulary, able, I've listed it in approximate alphabetical order here. The first word being A, second word is able, account, acid, across, and so on. And you just assign them in a number in alphabetical order, A being 1, able being 2, account is 3, acid is 4, and let's say the last word is zone, and you're going to be assigning the number 250,000 to this word, assuming zone is the last word in the vocabulary that you've chosen. This works. This is very intuitive for us to understand. This gives each word a unique ID, easy to identify. But there are some very fundamental problems. We cannot use this encoding. It's useful for certain aspects, but it's not useful for natural language processing tasks. The reason is this. Let's say you're trying to classify or predict a word, right? And when you're trying to predict a word, and let's say your natural language, your neural network is predicting, is trying to predict the word acid is number 4. But then let's say it misses by a little bit, and instead of giving you the number 4, it gives you just a little bit off by saying it's 3, right? Because while you're doing stochastic gradient descent or while you're learning, you don't hit the exact target. You slowly go towards the accurate answer. So instead of 4, let's say it predicts 3. So what you wanted to see was acid, but now it predicts 3. Now, if you look at 3 and 4, these two numbers represent the word account and acid. These are completely unrelated words. This makes the error very high, right? Even though it was able to predict the ID fairly accurately among 250,000 IDs, the meanings of the words are completely different. So what we found was, what the problem with this is, we have assigned almost random numbers or IDs to words. And these, it looks random to the algorithm because it does not understand the alphabetical order, right? The alphabetical order A, B, C, D, E, F, G itself is kind of completely random, right? So there is no reason why the ID 3 should be close to 4. That is why the word account should be very close to acid or across. These 3 words are completely unrelated, but they are very close to each other. This makes things very hard for many machine learning problems, and this could affect your learning process, and it might never converge, right? So we need to make sure that words that are closer together have some kind of similarity. Either it means something similar, or it shares some kind of context, or there should be some meaning. It should be intuitive in ways, at least in some way that's relevant to the machine learning task. This kind of encoding is never used, right? So this is useless. So then we can do what we can usually do is go to something on the other side, right? The other end of the spectrum, that is what is called one-hot encoding. Let's look at what one-hot encoding is, right? Again, you have the same set of words. So for each word, again, you're trying to assign an ID or an encoding or embedding. So what we do is we take a very large vector of almost all zeros except for one. There's going to be just one number that's going to be hot. That's why it's called one-hot encoding, where just one number is going to be 1, the rest is all zeros. And this number, that's the one that is actually hot, is the number of the ID of the word. That is A. We gave the integer value of 1, so the first digit or the first dimension is 1. And similarly, the word able is number 2, so second ID is 1, third number is 1, fourth number is 1, and so on. And for the last word, you would have the last digit or last dimension as 1. So now we've solved the problem of not having very dissimilar words close together. So this way, we've given each word a different dimension, right? So if you take each column in this vector as a dimension, each word is in its own dimension. So there is no confusion as to which word is closer to each other. All words are equidistant to each other, right? If you take the distance between A and able and A and account, or accident account and accident cross, they're all equidistant, right? So there is no problem of having dissimilar words very close together. Well, but there is a different kind of a problem here. The problem is that there are too many zeros, right? So each word was just a word. If you represent ASCII, was just like few bytes. Now this is now represented in a very large vector of size 250,000, or whatever the size of the vocabulary there is. People usually take anywhere between 50,000 to 400,000 words in the English language. So that is a very large vector. The problem with this is inherently is not a problem, but is more of a practical issue. The practical issue being you have limited memory size in your servers. Wherever you're running your machine learning trainings, the memory of this is going to be limited. And so when you are going to be limited in memory and you're using so much memory to represent just one word, this is going to cause inefficiencies in your machine learning training. And your training is going to be training very slowly. It's going to be converging very slowly. Each epoch of your training is going to take much longer time. So this is more of a practical issue than a correctness issue now. So how do we solve this? So we solve this by having what we see here is that we see a lot of zeros, and there's just one dimension that has a value of 1. What if we can bring this dimension down to something much smaller? That is, what if we can use this? Oops, sorry. If we can bring this dimension down to something much smaller, like 200 dimensions or 300 dimensions, and have this as a dense representation of the word. What I mean by dense representation of the word is that this is called a sparse representation, where the values that are non-zero are very rare, and the most of the numbers in this vector are 0. But what if we can bring this down to the 250,000 dimensions to just 250, but have a non-zero number in each dimension? Now, as human beings, we cannot imagine a 300 dimension or 250 dimension values, but it's possible to create them. That is the exact way in which you want to create. That's the exact reason for creating the word2vec or the blazing text algorithm. All right. So what are the requirements for word2vec? Even if you have 250 dimensions or 300 dimension vectors, the vector should be meaningful, as in you still want to make sure that words that mean something similar, or the words that have the similar context, should be clustered together, right? And the distance between those words must be smaller compared to words that mean the opposite or mean something completely different, right? We want to have a dense matrix or dense representation. We don't want to see a lot of zeros, because that is wasting memory, right? We also want to make sure this is unsupervised, because we don't want to be having human beings sit and tag words to be similar. That is, we don't want to have somebody sit and say these are synonyms, these should be closer, because that causes problems. because when you have a human being intervene, it causes it's subjective, first of all. It's also very expensive. It's not scalable. So we want this to be like, just give this to a large corpus of data and let it learn by itself. It should be unsupervised, right? And the last part is should be somehow intuitive, right? Even if you're not going to be telling the algorithm what the words mean, the meaning of the words, or other details, this should somehow bring about the intuitiveness of this embedding, right? In a 250 dimensional space. So those are the requirements for this. And if you look at this is very stringent, or if you ask me, this is a very very strict requirements, and some of this is also very vague, as what does intuitive mean, what does meaningful representation mean. So this has been a tough problem to solve, and it has been solved very recently, a few years ago, by a seminal paper called the algorithm is called word2vec, that is words to vectors. So it's popularly called as word2vec, and blazing text is also based on this seminal paper. All right. So what is the word2vec mechanism? How can you have this make this kind of algorithm? When I first heard this, I thought this was like magic. This is madness. How can an algorithm do this? So this is how a word2vec setup looks like. So you first start with a large corpus of text, right? This is just text. This could be a bunch of novels, maybe news articles. You just bunch everything together. You just need lots of text. Then you set the parameters. You set the parameters. The most important parameter of this whole process is the dimensions. What is the dimensionality of the vectors? You want 250 vectors, 300 vectors. That is really up to the use case and the corpus and the language. By the way, word2vec is easily applicable across languages. It's not limited to just English language, except for languages that have a large number of words, like Chinese. This is easily applicable to most languages. So you set the parameters for the dimensions, and then you have an unsupervised learning problem set up. And just one second, I apologize. And that's it. You've set up an unsupervised learning problem here, and boom, you would generate the dense embeddings. So the magic is actually in the last step, right? What is this unsupervised learning problem? How do you set up, and how do you generate these dense embeddings? So the first thing is, we want to understand the pre-processing step. The first thing you want to do is it's what is called a skipgram pre-processing. That is, you take a large amount of text and you convert it into training samples. You're not going to be feeding a sequence of words into this. You're going to be using a neural network, a very shallow neural network, if you will, but you're not going to be feeding the sequence of words like we saw in the sequence-to-sequence model. This is more of what you're going to be doing is you're feeding bigrams or n-grams, or what is called skipgrams. The first example here, you might have heard about the sentence, the quick brown fox jumps over the lazy dog. And I think this is a sentence that has all the 26 alphabets. So the word, what we're doing here is skipgram. So if you take it's a moving window, and the first word of attention here is the. So if you apply the skipgram to this, what you're doing is you're creating word pairs. Word pairs, that is pairing this word with every other word, any other word in its vicinity. So the first pair here is the and quick, and you create the first pair, and the second pair is the and brown, and this is the first data set for the word the. And then you move your window, and now you're trying to find out the context for the word quick. And the word pairs here is the and quick, quick and the, quick brown, quick fox. So likewise, as you move across your corpus, you're going to be creating this context for each word. You would have a list of words that is coming across as commonly for occurring words that occur in the vicinity of each word. For example, let's take the word brown. You're going to be seeing a set of words that are always in the vicinity of the word brown, and that is what is the training samples for your that's going to be feeding into your neural network. All right, so that's the first step. The second step is now you're actually going to be using your one-hot encoding for this. One-hot encoding is first you convert each word into one-hot vector, and you're going to be feeding the word of attention here. That is, let's say the word quick is being used here. You're going to be feeding the input, one-hot encoded input, to this very shallow neural network. This neural network only has one layer, one hidden layer and one output layer, right? And you're going to be feeding the input word, and what you're going to be expecting is the context word at the output, and that is also in one hot form. So you're going to be expecting a one in for the word that represents that word, and you're going to be using the word doing backprop to make sure that you learn the weights that correspond to this. So I hope you guys get this setup. So let me explain this again. This is a very shallow neural network with one hidden layer and one output layer. The input to this is the context, the word itself in one hot encoded form. The output is the expected context word. That is, let's say if you use the quick brown, quick could be the input word and brown is the output, and you expect and you learn for this context. Important point to note here is that the output layers is equal to the vocabulary size, right? Because it's one hot encoded form, right? The output also you should have, in this case I'm showing you 10,000 words and 10,000 neurons because the vocabulary size is 10,000. As you can imagine, as your vocabulary size increases, the output neuron size is going to be also going to explode. The most important thing here is the hidden layer. The number of neurons here is exactly the same as the dimensionality of your choice. If you have chosen 300 as your output dimensions, you're going to have 300 neurons in the hidden layer. All right. So, but as you can see, this is also 10,000. You're going to be doing a very large matrix multiplication here to get this. All right. So I have one question that I'm going to be trying to address this before I move on. Why would we use a lot of the question from Chris is, why would we use a lot of memory? This data structure seems sparse, seems it can be compressed easily. A good question. So I think this is addressing the question about the problem with one-hot encoding. That is, you can compress the one-hot encoded representation and to have a more efficient representation and do matrix multiplication with that sparse matmul operations. However, even if you have the one-hot embedded representation, the problem still occurs is every word is equidistant from any other word, right? They all have their own dimensions. That being the case, it would definitely be better if we can cluster the words that are similar, that have similar context close together, as opposed to having them all in their own dimensions. So that is, and as you can naturally see, when you can naturally bring that down to 300 words, it does offer you much better advantage than applying a compression algorithm on a very sparse matrix. Okay, it does definitely offer advantages of several orders in magnitude. Okay, so coming back to this network, this setup, this is what we're feeding. And an important thing to note is once this neural network is trained, we actually throw away the neural network. We are not going to be using this neural network once the training is done. What we're actually going to be doing is once the training is done, once you pass through the entire corpus of skipgrams, we are actually only interested in the weights of this hidden layer. We take each word and we find the representation, the weights that gets triggered, and we create a table of this transformation. And once we have the transformation, we really do not need this neural network anymore. We just throw away this neural network. So we're only looking for the representations of the word. We're not really going to be using neural network itself after training. That's an interesting way to use a neural network. All right. So now that once you're done with this neural network, what you finally do is you pass each word, you convert each word into one hot encoding, you send it through the neural network, and then you would see the weights that that the middle hidden layer neuron gets. And you take this and you make this as the representation of the word. I've shown a 5-dimensional representation. This is a 5-dimensional representation is not sufficient to represent 250,000 words, but to make it easy to understand, I've given a 5-dimensional representation here. As you can see, there is almost no a value here that's 0. So this is what is called a dense representation, right? Almost every single digit is a non-zero value, and you can see that each word gets even the 5-dimensional space is a very high dimensional space for a human being to imagine. And as you can see that we've been able to convert a word to a very small dimensional vector. So this is called word to vector algorithm. A blazing text is Amazon's version of word to vector with some optimizations and for intended to be used for AWS. Okay, as simple as this. Now you have this, but this kind of, when I look at this looks a little random, right? These numbers look a little random. I'm not able to say anything if it's we've got one objective done, that is this is a dense matrix, dense representation, smaller dimension. I get that, but I don't see any intuition in this, right? It's not intuitive. Is it just random? Can I just assign random numbers for each dimension? Would that also benefit? Looks like it's not random. So okay, let me first tell you what we use it for. So now that we have word vectors, we now can use this as inputs to a machine learning task. If you have a deep learning, let's say sentiment analysis, or any kind of a machine learning problem, now first you convert your words into a vector, and then using this fact text or blazing text, convert this into vectors, and now you can pass these numbers as inputs to your neural network, and you would be getting an output as well. So this now has been now is in a nice form. But before we go into that, I want to see if it's like, is there any intuition behind this? Is there something that we can learn from these representations, right? Is this really random? Is there a pattern? So here is a sample of the words that are being displayed. This is what is called a TSNE plot. A TSNE plot is a plot that helps you visualize a high dimensional space. So what we've done is taken a 300-dimensional vector and reduce the vectorization, reduce the dimensions into 2 dimensions, and display it in some way, right? So this kind of captures the data points that are close together and data points that are farther away. This helps us visualize a high dimensional space with a human eye, right? So this is from one of the runs that I ran using blazing text. And let's look at some, you see that there are some clusters. There are some clusters in the bottom here. There are some clusters, but in general, this looks spread out. But let's zoom in a little bit more, right? If you look at the bottom part of this, if you can see the bottom part in here, can you see the words 5, 4, 2, 0, 3, 7, 1? Notice how, even though we have not told what these words mean, the fast text or blazing text was able to understand that these words occur in very similar contexts and was able to cluster them together, meaning that even 300-dimensional space, these words are very close together. Not just the numbers. These look at this area, right? The words here are American, British, English, German, Germany, French, France, Europe, European, Europe, America, countries, world, and country. That is also, as you can imagine, similar words which have similar meanings, and that are being clustered closer together. Another example is here. This is beautiful. That is, you have day, days, year, and years. This is beautiful in more ways than one. I'll show you this. Notice how day. So as you can see, this represents time, and then you can see more words like time period here. But notice day and days, and year and years, right? Notice the difference between day and days, and year and years, right? So as you can see, there's a relationship between the word day and days, and year and years, right? So one is a singular, and another is a plural of the same word, right? Notice the distance between these two, right? So what the intuition behind this is that, let's say you have two words that have some kind of a relationship, like man and woman. This is the masculine form of the word, of the noun, and feminine form of the word, king and queen. These two word pairs have similar relationships, right? Man and woman, and king and queen. And if you look at word2vec, or blazing text representation, the distance between the two words represented in this dimension, that is distance between man and woman, would be very similar to the distance between king and queen, right? If you go back here, notice how the distance between day and days is similar to the distance between year and years. I find that to be magical, right? This is what we want to, this is what makes this very intuitive for me. Right. So that how did this come about? Like how are you even able to capture this kind of information in word2vec when we did not tell the algorithm the meaning of the words or these relationships explicitly? So what it did is that the first thing is the context. When you go back to understanding the context, the words day and days or man and woman appear in similar context, so they would appear close together. The second thing is they would have similar kind of differences in the context as well, right? So if it's a plural and singular, the difference in the context words would also be very similar. So that is what separates them in the context. But what is this context I keep talking about? The context means the set of words that co-occur with these words, and that's what we've been using for the skip graph method as well. But how did the context? How did we even find the weights? How can we even take the weights of the hidden layer and use it appropriately? So here's the deal, right? The first step of your neural network, if you go back, I said that we would be sending the one-hot encoded vectors into the neural network, and we would have a matrix multiplication. We would do the feed forward through the neural network and come up with the output. And we are actually, once you're trained, once you're just trying to get the word vectors, we don't even care about the output layer. We only just send the one-hot encoded representation of the word and see the weights, right? How does it? What does it? How does it do it? This is how it does it, right? So here's a simple matrix multiplication, right? Here's the one-hot encoded representation of the word, and here are the weights. As you can see that when you multiply, it basically these two, this vector and this matrix, it selects this word, this row, right? This row is 10, 12, and 19, and then you take this number and then you continue to multiply for the next layer, right? As you can see, this layer, this row of this large matrix represents this word in some form, right? This is represented in some hidden form. We cannot really put words to it, or we can only get some intuition, but we do not know exactly what these dimensions mean because it's a 300-dimensional vector. It's shown as 3-dimension, but you can take this as a 300-dimensional vector, right? So this is the reason why we can take the hidden words or the weights of the hidden layer as a representation of this of this word. Okay, and that's what we do. All right. So okay, so that is that is word to vec, and that's the core of blazing text, right? So we now saw the foundations of the blazing text algorithm. All right. So second thing, now we're going to see some more problems with this algorithm. Look, we're looking at, like, once we have solved the main problem, now we come to the second level of problem, that is out of vocabulary handling. That is, let's say you have a corpus that you use for converting this vocabulary into a dense representation. But then now you start using this word to vec, and then you find that there are new words that are being used while after you've converted, and you did not get this word in your corpus. Or it could either be a new word, or it could be a spelling error, typo, or it could just be a word that was not present in the corpus. So now, how are you going to be able to handle this? All right. So before we go into this, I want to answer a few more questions. Right. Okay. The question is, how can we say the words 1, 2, 3, and 4 are in a cluster when we have reduced the dimensionality from 300 to 2? So the dimensionality from 300 to 2 is only for visualization, to give us an intuition of how to of where the data points are. This is more of for a human eye to view, and you can see obviously that the words here, even in this Jupyter notebook, are very close to each other compared to the words theory and field. Right? It's just for visualization. It's not a theoretical clustering. It's more for visualization, and that's what the TSNE does. TSNE is used mainly for visualization and for human beings to understand and interpret what the machine is doing. All right. So second question is, was multidimensional scaling used to get from 5 dimensions down 2 dimensions for the visualization? So this is, I'm not going to go into the TSNE algorithm. Maybe we can cover that separately. This goes into the depth of what TSNE does. All right. But TSNE is one of my favorite algorithms, and this has helped the community a lot to understand what it does. All right. When training the neural network to produce the weights, what is the representation of the correct answer being used to train the network? Is it the percent of skipped grams where the input word co-occurs with output? Let me read this question again. When training the neural network to produce the weights, what is the representation of the correct answer being used to train a network? Oh, the representation of the correct answer, that is the ground truth. I think the question is about this diagram. What is the representation of the output word? That is also one hot encoded output. This is also one hot encoded. The output layer is also one hot encoded. And that is because this is a softmax classifier. It gives you the output from 0 to 1. All right, so I'm going to move on, and we'll come back to questions at the end some more. But feel free to ask a question if it's relevant. I would be answering this in the middle as well. All right, so let's see what is we saw the intuition as well, and some magical properties of word to vec or blazing text. Now let's look at some finer problems. Now that we've gotten our main problem solved of having a dense representation, reduced dimensionality, and a fast conversion into this representation, let's look at out of vocabulary handling, right? So out of vocabulary handling is actually quite a serious problem. Actually, this happened in my previous webinar as well, where I used in the sequence to sequence, I gave the input text that was not in the vocabulary, and that ran into problems. But blazing text can handle this as well. But you may ask, like, how does it even handle? How can you handle a word that was not provided during the training process? Because we did a one-hot encoding of words, and if the word was not in the vocabulary, there's no representation, right? There's no dimension of that. There's no representation. How can you handle this? So the way to handle this is also based on another seminal paper. It's called subword detection. So instead of taking an entire word as one word, as a unit, as the basic fundamental unit of a word to vec, what we do is we take subwords. So if you take the word apple, you actually split this into multiple words. You take APP, this being the starting character, and the greater than symbol as the termination condition, termination character. You take, this is a window, you take AP, APP, APPL, APPLE, and then with the termination word, PPL, PPLE, PPLE, and so on. All right. So this gives you the ability to take parts of this word, and then you vectorize this. So this, what happens here is that this helps you with some kinds of out of vocabulary words. For example, if in case you did not include the word apples, which is a plural form of apple, in the original vocabulary, you would still be able to find that, hey, most of this word is it's kind of similar to apple, except for one character at the end. And so this, you would apply this to another word that's similar, and you would be able to get this you would still be able to vectorize this word and not just error out, right? You're not like completely out in the open. This is, you still can vectorize this. However, if for words that have no subwords, like this, let's say you have a like completely different word, that is going to be a problem for it. It would still try to find a vector, but that may not be as accurate. So obviously, for you to get a really good accuracy for accurate vector for a word, it's better to be part of the corpus than not being part of corpus. All right. So the next word is like blazing text is our implementation of word2vec. It takes in several of these. First, it borrows from word2vec, and then it has applied several different optimizations on top of this. And blazing text goes even further to actually add a text classifier as part of this algorithm. That is, instead of just converting the words into vectors, we can just straight go ahead, add this as next part. For example, this is usually how a pipeline works. You have a pre-processing step where you convert the words either into skipgrams, or you convert this into a certain form, and then you transform them into word vectors using blazing text. And then you would probably apply this to a classifier. You probably use a deep neural network or LSTM neural network for your classification problem, right? But blazing text combines this, also offers this as one-shot solver for this problem. So, but the way you set up the problem is slightly different. But of course, there's going to be some pre-processing. So your question would be, what is this pre-processing step that you would need for setting this blazing text classifier as a blazing text as a classifier? So it's as simple as this. So you're going to be providing a text that is, let's say it's a sentence here. You need to provide this in this form. That is, first provide the label. The label should be prefixed with the special character that is underscore underscore label underscore underscore, and the name of the label. Either it's represented here as 4, and then you provide the text, right? And each line should be represented like this, and you feed this as the input to blazing text, and that's all you need. And then you run, let blazing text run, and you classify your text based on the data that you've provided. As simple as that, right? This adds a layer and makes things much easier. So if you're looking for any kind of text classifier, and I would first ask you to look at this as the first problem, as the first solution, because this would literally take you minutes to try out. And once you can see the accuracy of this, and then you can further fine tune if you need a higher accuracy. All right. Let's look at the parameters. There are 2 important parameters that you need to look at. It's called continuous bag of words and skipgram. So skipgram is what we saw, right? So we give, let's say, a quick brown fox jumps over the fence, right? So the way we chose our setup, we set up our algorithm was that we provide the word, and we expect the neural network to predict the context of the word. For example, in this case, if the word is brown, we expect brown to be able to break A, we expect brown to break quick, we expect brown to break fox and jumps, right? So that is one way to set up the algorithm. That is not the only way to set up the algorithm. There's this other way to set up the algorithm that is the opposite. You can actually provide the word, context word, and once you provide the context word, you would expect it to predict the actual word, target word. So in this case, you would provide a quick fox jumps, and the expected word would be brown. Of course, this is exact reverse of the other setup. And there are certain subtle differences between the two, but overall, I don't think it matters. There are some differences in accuracy for this, but in general, skipgram is preferred, and it's easier to understand. It also gives a slightly higher accuracy, but this is a parameter that you can set and see in your case whatever works for your case. But this is a parameter for you to set, right? Also, the most important part of blazing text is that it's been customized, optimized for AWS to be able to run in the hardware to use GPUs. And here are the options. You can run in single CPU instance for both CBOW, that is continuous bag of words, and skipgram. And there are also more versions, batch skipgram and supervised. Supervised learning is what we saw as a text classification problem, right? There is also single GPU instance. You may want to check to see if your combination of parameters can be using this GPU, right? Notice that the multiple GPU instances for you to do this, it works only for batch skipgram. So the reason this algorithm does not use GPUs all the time is that there are some optimizations that we have to apply for this to converge quickly, right? It typically usually takes only a few minutes to run. And if that is the case, they have applied several very interesting, very creative ways to optimize this, called subsampling, phrasing, and those are harder to be run on a GPU. And so only certain parameters, when you check, are going to be able to run on multiple GPUs. And batch skipgram is probably the most optimal that can run on this is multiple CPUs, but GPUs, yes. So I would ask you to look at the documentation to see the combination of parameters that can run on GPUs. Okay. All right. Now let's look at a demo of this. All right. The first demo I have is the blazing text words, right? So this is also one of the sample. Let me reduce the font so it fits into my screen. The blazing text. This starts with setting up your SageMaker, you're importing Bodo3 JSON and so on, setting your roles and so on. I'm going to skip this. Downloads the data set, and you want to be using the right container. And here's some documentation. We're going to be setting up the training. Here I'm using C42 extra large, 2 instance types. And this is the setting up the training job. Here are the hyperparameters for my job. That is, I'm going to use only 5 epochs. And sampling threshold is this. And most important for any word-to-vec blazing text is the vector dimensions. Here I've chosen 100 vectors, 100 dimensions. And you can check out the subwords is false. I'm not going to be using subwords in this training. And then I run my training, and it took just a few. Takes about 300 billable seconds to complete this job. And you can see that the words here are awesome and blazing. And this it converts this awesome. Let me try to run this one more time. I've deployed this model, this as well, and to get my result, I hope my network connection is still going. Right, and it's going to give me a 100 vector, 100 dimensional vector. I'm not sure what happened here. It was working like 2 minutes ago, just before starting up this webinar. I think I might have lost the connection to the server. Okay. So the most important thing of this is the plots, right? So I plot this a sample of the vectors using TSNE plot, and this is a plot we saw as well. Let's look at a little zoom in here, right? This is my favorite part. We saw the numbers. We saw how this is clustered compared to the other words. The other area that I want to focus on is also this. You guys can see this: the day and days, years, and age. This is clustered as well as the distance is maintained. All right. Let's look at another place. You can see here you have these words north and south and east and west. As you can see, the words north and south is much closer, and these two are paired, and these two are paired, and the distances between these two words is similar to distance between these two words. I find that to be beautiful, a beautiful example of how it has captured the meaning of the word, of the words, and the relationship between the words, even though it was an unsupervised problem. All right. Here's another. I think this is more of a corner case where it found several individual characters, and this is also clustered somewhere outside. Another example is over here: book, published, written, and so on. All right. So that is the first example of generating did one? Okay. Generating the TSNE plot of the high dimensional vector, or the word vectors. All right. Second case is, oops. All right. I think that is what happened in the others. Hold on while I refresh this page. Oops. I apologize. My session has expired. I go to my AWS console. I go to SageMaker, notebook instances. And what we saw was, the first one was the blazing text word to vec. Let's look at the subwords now. So subwords is very similar. Another notebook, example notebook, that's very similar, except that now you're going to be saying that while you set up your hyperparameters for the training job, you're going to say the subwords is true. That is all you do. Of course, you need to understand that enabling subwords equals true actually makes the it takes longer for the blazing text to run. As you can obviously imagine, there's more work to be done there, so it takes longer. So be aware of that. And this also takes, but it only took slightly longer, 330 seconds. And I also deployed. I'm hoping that this was. I am hoping this was done. I think I have. Okay, I have lost my session. But I can try to see this. So in this case, what I was trying to show was the words. I was trying to find a new example. In this example, I have the words awesome, and in this case, I have a spelling a typo, AWWEESOM, and in this case, it would still be able to generate this a vector for this word, even though this word was not part of the original corpus. All right, I'm going to try to see if I can run this notebook, even though I've lost it. I apologize for this. Okay, here's my. All right. So, all right. Here's my word. Actually, there's one more thing to note here. So here I'm trying to get the vector for the word awesome. This is again looking at the subword example. That is awesome, and you have a 100 vector size 100, right? You see some numbers here: 0.09, negative 0.12, 0.11, and so on. And now let's try the word awesome, which is not in vocabulary. And you would notice that there are. Let me make this smaller so that you can see, visualize the amazingness of this, right? You might notice that this is generated a vector, and you may notice that the vectors are similar. It's not the same. The awesome, as you would assume that as a human being, you would understand that this is just awesome with a typo. But the word2vec does not know this, so it generates a vector, but the vector is very similar to the word awesome. If you can see this is negative 0.09, this is negative 0.05, minus negative 0.121, this is negative 0.15, 0.11, 0.11, negative 0.1, negative 0.09, negative 0.25, and so on. As you can imagine, it's tried to do its job and produce a vector that's similar to the original word. So this subword is very useful for these kinds of use cases. All right. So the last one I want to show you is the text classification that I mentioned to you, right? Where you don't convert the words, you're not interested in the word vectors. You're only interested in the classification problems. So you can set up automatically with blazing text, right? So again, it's kind of setting up similar. And here, what you're trying to do is for each sentence, the classification is these, right? It's the sentence. What you're trying to learn from this is trying to learn what the sentence is going to be talking about. That is, the class is company. It's talking about educational institution, artist, athlete, and so on. And in this case, it's learned. I've already done the processing, I think. And the only important parameter that you need to do is you should set the mode to be in supervised mode. Word2vec or blazing text is generally an unsupervised learning problem, but we've now added one more layer of making this into a classification problem. So this is, they set the mode into supervised mode, and what you need to do is set the data to be, pre-process the data to be in this form. As I showed you, label, underscore, label, underscore, and the label, the name of the label itself, and then the text. So in this case, we've learned about 10 different classes. And let's run this example. Let's see if it runs. All right. So the first, we're going to be passing two sentences here. Convair was an American aircraft manufacturing company, which later expanded to rockets and spacecraft. And we passed this into blazing text model that has been deployed. And you can see that the label it generated was company. As you can see, this is about a company called Convair. The second sentence is Berwick Secondary College is situated in the outer Melbourne metropolitan suburb of Berwick. And that would be label, it is generally label of educational institution with the probability confidence of 0.99. So that is the three variations of blazing text, that is converting words to vectors and with a dense representation. The second is also adding subwords detection to produce vectors for out of vocabulary words. The third is even making it into a supervised classification problem that is that makes it much more useful, and one-shot text classification solution for one-shot solution for text classification problems. And the last one that I did not show you was that it can also use an existing representation and load that as and use the pre-existing word2vec neural network. So that's also provided. I'm not showing you that today because that doesn't usually show you what the algorithm does. All right. So please get started. To get started, I would recommend you to go to the documentation for blazing text. There is also a blog on blazing text. So feel free to read those. All right. So now I'm going to be opening up for, I think I used up 1 hour. I'm going to be opening up for questions. Chris, are there any questions that you would like to ask?
Sure. There's one question here that was unanswered from earlier before. How large would the data set need to be in order for a blazing text to work properly?
Oh, very good question. I think it's very relevant. Typically for any a word-to-vec or NLP problem, this depends on the vocabulary size, right? For English language, the vocabulary size can be anywhere between, depending on the corpus, can be between 10,000 words, which is on the lower end, to 400,000 words. And if you have such a large vocabulary size, you need to have a fairly large corpus as well. That is, you would need to have at least 1,000 or above use of each vocabulary, each word in the vocabulary, and that would help the word-to-vec to effectively learn the context. So the problem is that if there's a problem called hapaxes, right? Hapaxes are words that occur only once in a corpus. That is, if you give a word that occurs only once, as you can imagine in some literature, these are very rare words or maybe technical words. It has only one context, right? It has one usage. Even as human beings, we cannot learn the context, the meaning of the word with just one context. So it's important to have. It's not the size of the corpus; it's more about the usage of the of each word in the vocabulary. It needs to occur a certain number of times, enough number of times for the word-to-vec algorithm to work.
And this is not posted by an attendee, but if there are questions from attendees, please do enter them in the question area. Can you tell me, let's talk about use cases. If you don't mind, what are the most common use cases, and are there any non-NLP use cases?
Sure. So the blazing text can only read words. So a word-to-vec in general can be used to apply to convert a large dimension into a smaller dimensional dense vector. It's called any-to-vec. So we have products-to-vec algorithms. We have images-to-vector algorithms that all work in the same or similar way. That is taking a large, very sparse, high-dimensional data point into a smaller dimensional dense representation. But blazing text itself is a very NLP-oriented algorithm. It can only take words as inputs. That's the first one. The second one is that what are the typical use cases? The typical use cases are machine learning problems like classification, right? Text classification, sentiment analysis, right? If you have a bunch of text that you say have positive, negative sentiments, and you have a string, you can use word-to-vec. You have to pre-process using word-to-vec or blazing text before you pass it on. And we saw that how even blazing text can itself do the classification for you. The second important one is natural language generation, or what we call sequence to sequence, for which sequence to sequence can be used. That is, you instead of classification, you're now using this to generate another kind of text, right? So either you're paraphrasing, or you're summarizing, or you're doing something else, or maybe you're translating, right? In all those cases, you need to first use word-to-vec or blazing text to convert into vectors, and then only do any the NLP processing. This is to be honest, this is very standard, very well known. It's now become a very common practice to do this. Or actually, it's actually quite impossible to work with any NLP task if you do not convert the words into vectors.
And one last question just popped up here, and we're over the hour, so we should probably wrap this up after this one. Does document size matter? I think you may have addressed this. For example, is there a minimum number of words per document for the algorithm to be most efficient?
Yes. So it's not the document size, but the context and the use of the words. So if you have a large number of words in your vocabulary that are used very, very sparingly in your corpus, for example, like the word, a very technical word like cardiac I can't think of a word now, but a very technical medical term, right? Like let's say the word meningitis. It's a disease of the brain, a very serious disease. But let's say it doesn't appear in the corpus more than once. Now that word, its representation is not going to be very good. The accuracy is going to be low because it just doesn't know much about the word. So what we would actually do is that in some of the algorithms, we would run a pre-processing step where we actually remove the words that occur less than 10 times. And so that we can focus on the words that occur a large number of times. And so that is, yes, to answer the question, yes, the number of times a word occurs in different contexts matters, and that affects the corpus. That affects the accuracy of the algorithm itself, and going beyond accuracy, the core of the algorithm itself, the mechanism.
All right, well, thank you very much, Pratap. Sue, maybe you want to take us out?
Well, are there any other questions? Because we've got, we've got a few more minutes. I just wanted to make sure there weren't any other questions that you've got in the queue.
I have questions.
Well, I say let's go for it. I mean, we've got.
So you know, Pratap, just to share a conversation you and I were having just before this call. If you have a corpus of sommelier recommendations for particular wines, would there be a relationship between the descriptions of a wine and perhaps a recommendation system that you could create, you know, based on those, on the words in the recommendations? Or they're not even recommendations; they're just descriptions, sommelier descriptions of wine.
Sorry. So what are the two things you're connecting? The description and what?
Sure. What I'm asking is, can you create a recommendation engine using this if you had a corpus of sommelier recommendations, for example?
Somewhat recommendation? Sorry.
Oh, I'm sorry. So sommelier is a wine expert, somebody who tastes wine and says what it tastes like. What I'm saying is, if you had that particular corpus, could you use blazing text then to create a recommendation engine?
Oh, absolutely. So as you can see that the words, this should be applied in a slightly different way. We saw how the words with similar context appear close together, right? And you can actually cluster wines based on the description, right? I mean, recommending a wine could be done in several ways. This could be done based on the food that you're having. Certain wines go with certain food, and certain wines might go with certain time of the day or something of that sort. I'm not going to go into those connoisseur aspects of this, but more about the description. So what can we do with the description? We can actually do what is called a document clustering, right? So if you have multiple pieces of text, we can actually cluster these texts into a smaller dimensional space, just like how we saw. And based on the name of the wine, maybe the other parameters like location, the year, the description, and you can add all those things and convert that into a lower dimensional space. And when you look at the TSNE plot, you would notice that similar wine might be clustered together, right? And if you're converting that into a recommendation engine, like a problem, what I would recommend is if a person likes a wine of a certain kind, I might be able to recommend things, other wine that are close together in that cluster.
So there's two more questions here, and this looks somewhat related to what you were just describing. Can blazing text give us some sense of entities and relationships in the corpus through their vector representation?
That is a tricky question. I should say yes or no. So first of all, entities in words, that is, if you look at a word, if you look at a sentence, you can consider parts of speech tagging as one kind of entity, right? For example, even in this example that I showed you, they were looking at the subject of that sentence, whether the subject was both educational institution or a company. Parts of speech tagging or any kind of entity is not possible with blazing text, right? It does not directly give you that. There are separate other algorithms for that, but this blazing text cannot be used. You can use this as first step before you send it into for processing, but by itself it does not give you that. That's one. The second thing is, I think if I understood the question right, are there any meanings in the dimension itself? Let's say if I have 5 dimensions, do the dimensions really mean something? I'm going to say no. This is a personal opinion. I don't think there are some opinions out there about the meanings of the vectors itself. To me, and I don't think there's any a general concurrence on what this means. If you look at a 300 dimensional vector, I don't think the 300 cannot be directly applied to features of a word, right? It cannot say the first dimension means it's a verb, second dimension means it belongs to a location. I don't think it works like that because these dimensions this is a stochastic process. That is, the dimensions you could change from 300 to 301 dimensions, and everything could be like completely different, right? So the dimensions themselves do not have any meaning.
So I think the next question would be, when are we going to cover latent Dirichlet allocation, right? I think that is coming up on our list of built-in algorithms. So the next question, yeah. So could blazing text?
I can bring up the date for that LDA.
I'll read the question here, Pratap. So could blazing text be used to identify questions? Oh, I'm sorry, to identify quotations in text and the references associated to those quotations?
Can it identify quotations, and can it identify the references in that quotation? I think I understand the problem, but we have to be careful to say that if this problem can be converted into a machine learning problem, that is, it's either a classification problem, that is, if given a text, can I classify this as either a quotation or not a quotation? I think that problem is solvable just by using blazing text classification. We have the right data to train it on. And can I find the reference that the quotation is trying to say? I think that might also be considered a classification problem. If it can be converted reduced to a machine learning problem or even a classification problem, and if you have the right data, I think it's possible. But I don't think I can just wave. I'm hand waving here to see that there are many corner cases that could fail, and so I'm going to be a little careful in saying it's possible. I think it's promising, but I have to know the details some more.
All right. I don't have any more questions, and I don't see any more coming in.
Excellent. Pratap, thank you so much. And Chris, thank you as well for helping us get through the questions. To everybody who is still on the call, thank you for hanging in with us. I know this was a meaty topic and also a really cool topic. We are going to follow up this cool topic with an even cooler topic next week. And so just 1 week from today, we are having a kind of a special and unique topic that we're popping into this SageMaker series. It's not specifically addressing any SageMaker algorithms by name. We're covering a bunch of them actually. We have a prototype that was built by one of our internal teams to address optical character recognition. And so we thought that was a topic that would be of interest to a lot of you. So take a look at, actually I popped the registration link in the chat, but you're also going to get an email in about the next 6 hours. It's going to have a link to the replay of today's call. So if you want to dig back through this content, you can do that. And it also has a link to that next week's webinar. So be on the lookout for that. And we look forward to seeing you all again in 1 week. So with that, we'll end the call and wish everybody a fantastic rest of your day. Thanks, everyone.